So, what exactly is the deep sea? Scientifically, it typically refers to the ocean waters and seafloor below 200 meters, or about 650 feet. This depth marks the boundary where sunlight can no longer penetrate, creating what scientists call the aphotic zone. Above this, we have the photic zone, where photosynthesis can occur. But below 200 meters, there's no light for plants to grow, forcing life to adapt in truly extraordinary ways to an environment of eternal night. One of the most profound challenges of the deep sea is the immense hydrostatic pressure. This is the weight of the water column pushing down from above. For every 10 meters you descend, the pressure increases by about 1 atmosphere, roughly the weight of a small car. At the deepest points, the pressure can be equivalent to stacking 50 jumbo jets on your thumb, or having 100 adult elephants balance on your head. Creatures living here have evolved incredible adaptations to withstand this crushing force. Beyond the pressure, the deep sea is defined by two other formidable conditions: perpetual darkness and near-freezing temperatures. With no sunlight to warm the water, temperatures often hover just above freezing, typically between 0 and 4 degrees Celsius. The absence of light means there's no photosynthesis, which is the primary energy source for most life on Earth. This lack of light and warmth demands unique survival strategies, turning the deep ocean into a cold, dark, and utterly silent world for much of its vast expanse. For centuries, our understanding of the deep sea was limited to creatures accidentally caught in fishing nets or washed ashore. Early attempts at exploration in the late 19th and early 20th centuries involved dredging the seafloor or using cumbersome diving bells. These methods offered tantalizing but brief glimpses. Scientists knew there was life down there, but the technology simply didn't exist to explore this vast, hostile territory safely or effectively. It was a realm of pure speculation, fueled by strange, preserved specimens. The mid-20th century brought a revolution in deep-sea exploration with the development of robust manned submersibles. Vessels like the Bathyscaphe Trieste, which in 1960 carried 2 men to the deepest point in the ocean, and the iconic DSV Alvin, launched in 1964, finally allowed humans to witness these alien landscapes firsthand. These pioneering crafts, equipped with powerful lights and cameras, were the first to truly peel back the curtain on the deep ocean, allowing scientists to conduct direct observations and collect samples. While manned submersibles are invaluable, much of today's exploration is carried out by robotic pioneers, remotely operated vehicles, or ROVs, and autonomous underwater vehicles, AUVs. ROVs are tethered to surface ships, controlled by pilots, offering real-time data and precise manipulation for sampling. AUVs, on the other hand, are pre-programmed to explore independently, mapping vast areas of the seafloor for extended periods. These robotic explorers allow us to reach places too dangerous for humans, transforming our ability to study the deep. One of the most astonishing deep-sea discoveries came in 1977 with the finding of hydrothermal vents along the Galapagos Rift. Scientists in DSV Alvin stumbled upon towering chimney-like structures spewing superheated, mineral-rich water from cracks in the seafloor. These hydrothermal vents were not merely geological oddities, they supported vibrant, dense communities of life. It was a revelation, showing that complex ecosystems could thrive entirely independent of sunlight, challenging fundamental biological assumptions about Earth. The life around hydrothermal vents relies on a process called chemosynthesis, not photosynthesis. Instead of using sunlight, specialized bacteria convert chemicals, particularly hydrogen sulfide from the vent fluids, into organic matter. These chemosynthetic bacteria form the base of the food web, much like plants do on land. They are consumed by other organisms, or live symbiotically within them, providing a unique foundation for life in an environment that otherwise seems utterly inhospitable, forever dark. Around these vents, life flourishes in an abundance previously thought impossible for the deep sea. Giant tube worms, some growing over 2 meters long, have no mouth or gut. Instead, they host symbiotic chemosynthetic bacteria that provide them with nutrients. Blind shrimp, mussels, and crabs also thrive here, forming complex food webs. These vibrant deep-sea oases demonstrate life's remarkable ability to find a way, even in the most extreme corners of our planet, sustained by Earth's internal energy. Beyond the abyssal plains, the ocean floor plunges into colossal canyons known as ocean trenches. These are the deepest parts of the ocean, formed at subduction zones where one tectonic plate slides beneath another. They are not merely deep holes but vast, steep-sided valleys that can stretch for thousands of kilometers. These geological wonders represent some of Earth's most dynamic and least explored environments, with pressures that dwarf even the crushing forces found in other deep-sea habitats. The most famous and deepest of these is the Mariana Trench in the western Pacific Ocean. Within this trench lies the Challenger Deep, the deepest known point on Earth, reaching an astonishing 10,928 to 10,984 meters, or nearly 7 miles, below the surface. If Mount Everest were placed in the Challenger Deep, its peak would still be more than a mile underwater. The pressure here is over 1,000 times that at the surface, a truly mind-boggling environment for life to endure. In the perpetual darkness of the deep sea, light is a precious commodity, often created by life itself through bioluminescence. This is the chemical production of light by living organisms, and it's incredibly common in the deep ocean. Creatures use bioluminescence for a myriad of purposes: to attract mates, lure prey with flashing beacons, or even evade predators by startling them or creating a defensive smokescreen of light. It transforms the dark abyss into a spectacular, living light show. The deep sea is home to an incredible array of creatures, many of which appear truly alien. Take the anglerfish, famous for its bioluminescent lure that dangles in front of its cavernous mouth to attract unsuspecting prey. Or the vampire squid, which uses its webbed arms to engulf victims. The colossal squid, with eyes the size of basketballs, is another giant that roams these depths. Each species showcases remarkable adaptations, from extreme vision to gelatinous bodies, allowing them to thrive in these conditions. The deep seafloor is not static, it's a dynamic landscape shaped by powerful geological forces. Mid-ocean ridges, like the Mid-Atlantic Ridge, are vast underwater mountain ranges stretching for tens of thousands of kilometers. Here, tectonic plates pull apart, and new oceanic crust is continuously formed as magma rises from Earth's mantle, creating new seafloor. These seismic hotbeds are often where hydrothermal vents are found, linking the planet's internal heat to deep-sea ecosystems. Deep ocean exploration is an ongoing, vital scientific endeavor. Research vessels equipped with advanced sonar, ROVs, and submersibles embark on expeditions globally, constantly mapping new areas and discovering new species. For example, recent missions have uncovered vast deep-sea coral reefs and sponge gardens, thriving in cold, dark waters. Each expedition brings us closer to understanding the biodiversity, geological processes, and crucial role the deep sea plays in regulating Earth's climate and supporting life. Despite technological advancements, deep-sea research remains incredibly challenging and costly. The immense pressures, freezing temperatures, and vast distances require highly specialized, robust, and expensive equipment. Maintaining research vessels, operating submersibles, and funding multi-week expeditions demand significant resources. Scientists must plan meticulously, as even small technical issues can derail months of preparation. This makes every piece of data and every new discovery a testament to human ingenuity and perseverance in the face of nature's extremes. Despite its remoteness, the deep sea is not immune to human impact. Emerging threats like deep-sea mining, which seeks valuable minerals, and the pervasive problem of plastic pollution, increasingly reaching the deepest trenches, pose significant risks. Climate change also affects deep-sea currents and oxygen levels. These ecosystems are often slow-growing and incredibly fragile, meaning damage can be irreversible. Protecting these unique and largely unknown habitats is a crucial conservation challenge for our generation. The future of deep-sea exploration is bright with promise. Next-generation robotics, artificial intelligence for data analysis, and advanced sensors will allow us to explore even more efficiently and broadly. Miniaturized submersibles, capable of operating in extreme conditions, are also on the horizon. Beyond Earth, understanding deep-sea life helps us consider the potential for life on other ocean worlds in our solar system, such as Europa or Enceladus, making deep-sea research a key part of astrobiology. The deep sea remains Earth's last great frontier, a realm of unparalleled mystery and wonder. From the vibrant oases of hydrothermal vents to the crushing solitude of the Challenger Deep, it challenges our imagination and pushes the boundaries of scientific inquiry. Each discovery reminds us of the planet's incredible complexity and the resilience of life. As we continue to explore, we deepen not just our understanding of the ocean, but of Earth itself, and perhaps even our place in the universe.